Okay. We are talking about free resolutions, right? And so I finished last time by giving you an example of a free resolution of this module. So first of all, the underlying ring is the polynomial ring in 3 variables x, y, z. And the module is the ring mod out by the ideal generated by x, y, and z. Okay? And so we found that the generators for the module, then generators for the syzygies of 1, then generators for the syzygies of the syzygies, and then generators of the syzygies of the syzygies of the syzygies. Which here I'm calling M, sys 2, M, sys 3m. I should tell you that here I'm cheating a little bit because, like I told you, these exact modules depend on the generators that I chose. So, for example, sys 2 of m doesn't just depend on m. It depends on the choices that I made here. So bear in mind that maybe I'll put this in quotations so you know that I just don't want to write the syzygies of the syzygies, etc. And then I told you that we can, basically that this tells the story of how the module is generated, then what are the relations between those generators, what are the relations between the relations, etc. So this kind of tells the story. And there's a way of summarizing that story, which is in terms of this thing that I wrote here, which is the free resolution of the module. Okay? And I want to define these things a little bit more carefully today. But maybe what I should say is give these things names. Okay? So I think I call these A1, then B1, B2, and B3. Then C1, C2, and C3. Well, no. Let's just try to keep the notation as clean as possible. Okay. Okay. So how are you supposed to think about this? Well, each one of these free modules has a basis, right? They're free, so this is generated by one thing, by three things, by three things, by one thing. And these maps are really, you can think of them as these are the transition matrices, and so these are kind of linear maps from, for example, from R3 to R3. So an element of R3 is a column vector of length 3. And when you multiply by this matrix, then you get something in here. Okay? Now remember that multiplying a vector by a matrix like this gives you a combination of the columns, which is a combination of the basic syzygies. And so that tells you that the image over here is going to be all the syzygies that live in here. Okay? Okay. So what am I saying then? Let's make some definitions. So this is kind of this is the beginning of a whole subject called homological algebra, but I'll tell you just some things that we will need. Okay? So I'm going to define two things for you: a complex and an exact sequence of R modules is a sequence of modules and homomorphisms that looks like this. So it's just something that looks like that, a row of modules and homomorphisms between them. Okay? So those are the modules, and we call the homomorphisms F. So we have for each n, we have a homomorphism Fn plus 1 that takes me from Mn plus 1 to Mn. Okay? So in general, I could consider this for any modules and homomorphisms, but we're going to call this either a complex or an exact sequence if, so it's a sequence of modules such that, and I'm giving you two alternative definitions, right? So what's a complex? Well, a complex is when you take the composition of these two maps, you get 0. Okay? That means that anything that I map from mn plus 1.
Is the camera on? Your mic on? And the lights are on. Recording.
So let's start from here. So, so I'm defining either a complex of R modules for you or an exact sequence of R modules. Okay? So that's going to be a sequence of modules and homomorphisms. So the modules are these M guys. The homomorphisms between them are these purple F guys. Okay? So I'm going to say that this is a complex when the composition of Fn and Fn plus 1 is the zero map, which means that if you take something and you map it to the next guy and then you map that to the next guy, you always land at 0. Okay, so that makes you a complex. And you're an exact sequence if the kernel of, when you consider the image of Fn plus 1, that's going to be exactly the kernel of Fn. Image of Fn plus 1 is equal to the kernel of Fn. Okay? So why am I making a parallel between these two definitions? Because think about what this is saying. This is saying that if you take something in here, in mn plus 1, and you use it to map, you map it to mn, then that's going to map to 0. In other words, that guy is in the kernel of Fn. Okay? So this condition is equivalent to saying that the image of Fn plus 1 is contained in the kernel of Fn. Okay? So saying everything that comes from Fn plus 1 gets mapped to 0 by Fn. Okay? So we're going to call it a complex if you have this containment, and we're going to call it exact if actually that's an equality. By the way, so I've heard some of you guys say before that you have no idea what a homology group is and that you're scared of homology groups. Well, a homology group is very easy to define at this point because this is these guys are abelian groups, right? I mean, every module is in particular an abelian group, and then it has an additional structure of R module. That means that these maps of modules are also maps of abelian groups. Okay? And so these guys are abelian groups, and if this guy is contained in this guy, then I can take the quotient. And that's what's called a homology. So I want to just write that down now. We won't use it right now, but we will use it in this class. So I want you to at least see this definition. So the homology groups of this complex, so maybe we'll call it C. Okay, so this guy is going to be called C. This is going to be the group kernel of Fn modulo image of Sn plus 1. Okay? This is supposed to be a kernel. But you see, to be able to define this, you need a complex so that you do have this containment and you can construct this. You can construct this quotient. Okay? This is a little bit of a parenthesis. We won't really need this right now. Okay. There's something else that you might have seen before, which is a short exact sequence. It's like that, but it's short. And it starts at 0 and it ends at 0. If you think about this, I don't really have a choice on what this map is because I have to map 0 to 0. And I don't have a choice for this map because I have to map everything to 0. So the only choices are what is this map and what is this map. Okay? Now, what are we going to demand? Well, the same thing. It should be exact. So that means that it needs to be exact at A, at B, and at C. Okay? So what does it mean to be exact at A? Well, I shouldn't use an arrow because you might think that's another homomorphism and get worried. What does it mean to be exact here? The image of this map is 0, and the kernel of this guy is the kernel of this guy. So what I'm saying is that the kernel of f is 0. In other words, that f should be injective. Okay? So f should be injective. That's what it means to be exact at A. To be exact at B, well, the image of f should be the kernel of G. And what does it mean to be exact at C? Well, the image of G is the image of G. Now, what's the kernel of this map? Well, everything gets mapped to 0. So the kernel of this last map is all of C. So what I'm saying is that the image of G should be C. In other words, that G should be surjective. Okay? So I'm not giving you a new definition. I'm just telling you that if the sequence looks like this, then this is a restatement of this definition. Okay? So that's this, and then my main definition is that a free resolution of M is an exact sequence that ends at M and such that everything else in the sequence is free modules. Okay? So R to the, we call this B0, R to the B1, etc. Okay? So that's a more formal definition of a free resolution. Okay. And really, you're thinking that you're resolving the module M through these different free modules. And that's what we have over here. Okay. So let's go back and discuss this example again. So here's a module, right? And we want to resolve it. And so a free resolution is that thing, but it also means exactly this process of taking syzygies. Okay? So we say, okay, well, the module is generated by 1, and that tells me, okay, the module is generated by 1. Now, the syzygies of M are generated by X, Y, and Z. Okay? And so I'm going to use these guys, X, Y, and Z, as columns. Okay? And I'm going to think of X, Y, and Z as syzygies living in R3, which is what we did last time. Okay? And so I'm going to think that basically this is kind of the home of a basis of syzygies, and the columns over here are going to be the syzygies. So this is the module, this is the map. Okay? I go to the next step, and I say, okay, well, the next guy is generated by these syzygies. Okay? These are the syzygies of these guys, and so I make those columns of my linear map, and then I keep doing this. Okay? And so what we did very explicitly in the last class was construct a free resolution. Okay? Now, think about this for a second. Why is this a free resolution? I kind of drew something and I put some arrows on it, but I should justify that this is indeed a free resolution. So first of all, at least we have the arrows, right, and we have the modules and we have the maps. So that's a start. But we need more than that, right? So what do we need? We need that. We need exactness. Okay. So for example, what does it mean to have exactness right here? It means that the image of this map equals the kernel of this map. Now I have explicit matrices here, and so really what I'm saying is that the image of this matrix is equal to the kernel of this matrix. Okay. Now, what is the image of a matrix? The image of a matrix is the combinations of the columns. And the columns are our basic syzygies. And so what that statement is saying is that the combinations of the basic syzygies give me all the things that kill this guy, which is the definition of a syzygy. Being in the kernel of this guy means being a syzygy. And so what I'm saying is that these three guys, the basic syzygies, generate all the syzygies. Okay? So I said it quickly, but make sure that you understand that. That what we're doing here very concretely is exactly what we're doing over there. This is an exact sequence. So the summary of this whole stuff is this free resolution. And implicit in saying that it's a resolution is that it's exact. And so we like to think that we resolved the module M using these free guys. Question?
Yeah. So I remember you mentioned before that those numbers, the 1, 3, 3, and 1, they're not arbitrary. There's a reason for why they're those numbers. Is it because it's like, well, like that 1 is like, 3 choose 0, and then like as you kind of go along, it's like then the 3 is like 3 choose 1 and 3 choose 2 and 3 choose 3 again. Like that's sort of the formula that determines those numbers.
Right.
Is that true?
So what's up with those numbers, basically, is what you're asking me. Why are they so nice in this example? We like the sequence 1, 3, 3, 1, because this is the third row of Pascal's triangle. So is this a coincidence, or is it not a coincidence? Well, it depends on the ring and the module. But now there's another thing that I should say here, which is that it doesn't just depend on the ring and the module, because like I told you, I put quotations here because these things depend on choices here. And that means that the sequence also depends on the choices that we made along the way. For example, if I added more generators to here, then I would be changing this diagram. So the numbers actually depend on the choices. Okay? But what I'm going to say next, or at some point today, is that first of all, there is kind of a best choice of a resolution. There's the smallest one. Okay? And for the smallest one, you can ask what the numbers are. And the answer to your question is that those numbers are nice sometimes. And sometimes they're not. And this happens to be nice, a nice module, and that's why the numbers happen to be nice here. In your homework problem, that's also a nice module, so if you do it carefully, you'll see that those are also nice numbers. But if you pick some random module, you're just going to get some random numbers, and that's what you should expect. Does that answer your question? Hopefully I'll answer it a little bit better throughout the class. But yeah. So here's the next thing that I wanted to state, which is a beautiful theorem due to Hilbert. Hilbert's syzygy theorem. It says that every finitely generated module over the ring, the polynomial ring in n variables, has a free resolution of length n. And what I mean by length is basically that this process, you can think of it in two ways. First of all, you can think that this is a finite sequence of maps. And you can also think of it as doing this process of syzygies, and that process ends. Okay? Now, this theorem, in principle, it's an amazing theorem because when we were doing this, it seemed pretty magical that it terminated, and we didn't know that it would terminate. It just happened to terminate. But the only reason that I was confident that the class wasn't going to last forever is that I knew Hilbert's syzygy theorem. I knew that because I started with 3 variables. After 3 steps, this thing had to end. Okay. Now, that's why I didn't choose an example with 7 variables, because then it would take me 7 steps to end. In the homework, you have something in n variables, and so you know that there should be a way to make it end in n steps. Okay? And that's why that's a reasonable question. So this is a great theorem, and like I told you, whether this sequence terminates or not really depends on what ring you're living in. So for example, if n is equal to 0, then you have no variables. You just have a field. A module over a field is a vector space. And we said that with vector spaces, this story is kind of irrelevant. You never have relations over your bases. Okay? So if you started with a vector space, in step 0 you're done. Well, that's a very silly special case of Hilbert's syzygy theorem. If you don't have variables, then you have a Fourier solution of length 0, which means you didn't need to do anything. But as you add more variables, this gets more complicated. And with n variables, you might need n steps. But that still means that these rings are relatively tame. They're relatively well behaved. But if I choose some random ring, then there's no reason to expect that this will terminate. And that's what problem 6 in the homework does. Is it gives you an example of a ring which is not very complicated at all, actually, but for which this theorem is not true. Sometimes you just can never end the process of taking syzygies. Okay? So that's Hilbert's syzygy theorem. Okay. Now, let's see. Maybe I'll ask you guys, are you excited about this theorem yet? Should I prove it, or should I tell you more things about why this theorem is a good theorem?
Tell us more.
Okay, I'll tell you more. I mean, I hope you agree that it's a nice theorem, but why should we care? I think that's a very reasonable question, and I told you guys that that's a question that you are allowed to ask. Why should I care? Well, maybe it's already beautiful enough for you, but maybe you want to apply it. So what's the point here? The point is also that modules, arbitrary modules, can be very complicated. We don't know. If I give you a random module, there might be very complicated structure. But a free module is very easy, because a free module is almost like a vector space. Okay? You really have a basis, and you have no relations between the bases. You understand those very well. So one reason why this is very nicely applicable, and we will apply it, is that many properties of modules are very easy for free modules. Free modules are simple. So many properties of modules are very easy for free modules. And they behave very nicely with respect to exact sequences. What I mean by that is that sometimes you can, if you have an exact sequence, you can propagate properties of the module. So for example, you might be able to prove something like, in an exact sequence, if A and B have a certain property, then C also has it. This is the kind of thing that is true for several properties of modules. And that basically means that if you can understand all of these guys, then you can propagate your knowledge of those guys into knowledge of n. Okay? And that I would say is the main philosophy why this is a useful thing. So I should say many properties are easy for R to the m, and I put in quotations, propagate along exact sequences. I don't know, probably for many of you, this is the first time that you see an exact sequence. But exact sequences appear all over mathematics, and they're a very useful tool, and I think you will see that as you go on. And this is, I mean, we'll see concrete instances of this statement, but this is kind of a general philosophy. So it reduces questions about general modules to questions about free modules. Okay. Okay. So let's go ahead and prove this theorem. I want to keep this. Let's do it over here. So this is a nice theorem, theoretically, but it would also be good if not only do we know that this free resolution exists, but if I also tell you how to compute it. Okay? And so that's actually what I'm going to do, is not only prove existence, but actually tell you how to do this. Okay? And here's a lemma that we're going to need. So suppose that we have a Grosvenor basis. Maybe first, before I write this, maybe I'll just tell you how you do this in practice, because I can explain it to you in words. Remember that when we did this, we made sure that this guy was a Grosvenor basis for this module. Okay? And then by Schreier's theorem, we deduced that these guys were a Grosvenor basis for this module. And by Schreier's theorem, we deduced that this guy was a basis for Grosvenor basis for this module. In other words, Schreier's theorem tells us that we can do this in such a way that at each step we have a Grosvenor basis. And so that at least is one way of doing this, except we don't necessarily know if this process terminates. Okay? So this is a way of constructing a free resolution, but it might not terminate. But what I'm going to tell you now is that you can make it terminate pretty easily. The only thing you might have to do is take these three guys, and maybe you didn't like the order that they came out in, and you might have to rearrange them. Why does that matter? Because, well, you'll see. It might seem very strange, but yeah, the point is, if you kind of carefully keep track of the order that we wrote these in, then we can show that this process actually terminates. As I say this, I realize that actually this process doesn't care at all what order I wrote these in, right? And so that must mean that what I'm going to prove to you is that this process terminates after n steps. It's the proof that depends on the order, but the process can't depend on it because I never used the order here. So that's what I'm going to do. Okay. So lemma, suppose that this is a Grosvenor basis, so you should think of this as, for example, the step of the second syzygy. So these might be y minus x0, z 0 minus x, and 0, z minus y. Okay, that's a Grosvenor basis in R to the m. So I'm going to ask you to order them in a way that I like. So arrange them to have the following property. And the property is that if the initial term of gi is some monomial ni times a basis vector eu, and the initial term of gj is some other monomial times the same basis vector, then the point is that the monomials ni and nj have an order because they're monomials, and we have a monomial ordering here. And so I want to list them in such a way that I is less than j if and only if ni is bigger than nj. Okay? So what do I mean in this example? Here, these are g1, g2, and g3. I take the initial terms, and the initial terms are y, z, and z like this. Okay? And I'm telling you, look at every pair that involves the same basis vector. Okay? So this pair occurs in the first coordinate, so I need to worry about that pair. And what I'm saying is that because this guy is y and this guy is z, and y is bigger than z in my order, I guess I had said that earlier, right? Y is bigger than z, and so I should list this guy before I list this guy. It's just a matter of rearranging, right? You can definitely accomplish this. And because these guys are in different coordinates, you don't care. And these guys are in different coordinates, so you don't care. The only pair you worry about is this. You list it in the right order, which is what I did here. So if I do this carefully, so if I satisfy this property, then I have the following property. That if the variables x1, x2, up to xs are missing among the initial terms of the GIs, then the variables x1, x2, xs up to xs plus 1 are missing among the initial terms of the syzygies, tau ij. Actually, I'm realizing that I said something slightly wrong here. Ni and nj, you're going to compare them not according to whatever monomial ordering you're doing things in, but according to the lexicographic order. Okay. And so what I'm saying is, once you've computed your Grosvenor basis, you're just going to rearrange it so that it looks, you just alphabetize it, basically. You alphabetize each Grosvenor basis. And if you do that, then you have this property that maybe looks a little bit strange. Let's see what it's actually saying. What is it actually saying? Let's kind of propagate it along this path. Okay. So for example, here, this lemma might be referring to this situation. These are G1, G2, and G3. These are the initial terms, and there are no variables missing from those initial terms. Okay, so that means that no variables are missing among the initial terms of GI. So that tells me that x1 will be missing among x1 will be missing among the initial terms of the syzygies. In other words, if you look at this initial term, and this initial term, you're not going to see the letter x. Okay? So that's good news. It's definitely what we see. You go to the next step and you say, okay, well, here in this initial terms, I'm not seeing the letter x. So what this is telling me is that in this term, when I take the initial guy, I'm not going to see the letter x, I'm not going to see the letter y. Okay? And you see it, it's a z, right? Then in the next step, the initial term is not going to have any x's, it's not going to have any y's, it's not going to have any z's. So what is it? It's 0, right? And that means we're finished. So that's going to be our proof. It's a nice proof. I like it. It's very, very explicit. I say, well, I'll say that more carefully in a second about how this proves Hilbert's syzygy theorem. But let's prove this lemma, which is not too bad. You just have to remember something. And I don't know. Do you remember what this initial term was? I wrote it in a big box when I made this proof. So when I proved Freier's theorem, I said that this initial term was going to be 0 if these guys involve different letters. Okay, it's kind of dangerous to call them U and V. They're not going to look very different. Let's call them V and W. Okay. And if these guys involve the same EU, then I proved that the initial term of this guy was just going to be this thing that we called MJI EU, where MJI was this thing that we got from what's the name, from Bookburger. Okay. So I proved this. I proved this last time. This is the initial term of a simple syzygy ij. It's 0 if gi and gj involve different e's in the initial term, and if they are of this form that I said here, if they involve the same eu, then the initial term is just mji eu. Okay, that's the formula. And so what I need to show is that I don't see any of these letters from x1 up to xs plus 1 here. So one to show, okay, this is one to show that there are no x1s, xs's, and xs plus 1s in this expression. Okay? This is what I need to show, because that's the initial term. Now, if you think about it, this comes for free, because ni, n, and j are the initial terms of gi and gj. We're assuming that they don't involve the variables x1 up to xs. Okay, so this doesn't appear here, and it doesn't appear here, so there's no issue there. Okay, these don't appear in the ni, so there's no problem there. But now I need to justify that that letter x, s plus 1 disappears. Okay? Why does it disappear? Because let's assume that it doesn't. First of all, if it doesn't exist in ni, n, and nj, then there's nothing to prove. Okay? So let's assume that this letter xs plus 1 appears either in the numerator or in the denominator. What I'm claiming is that it's going to cancel. Okay? So let's suppose that ni involves the letter xs plus 1 and then some other letters, and nj looks like this, where what's the point? The point is that ni and nj don't contain any of the letters up to s. So this is the smallest letter that appears here. Right? All these other letters are greater than s plus 1. Okay? Well, then, what does the LCM of ni and nj look like? Well, it's the LCM of these monomials. And so what is the power of xs plus 1 here? Well, it's the larger of these guys, right? So if you want the least common multiple, you need to take the larger of these guys. And then there's some other garbage. Okay. But what's the point? Well, the point is that I haven't used this lexicographic property, right? I is less than j, which tells me that ni comes before nj lexicographically. Okay? And so what that's saying is that because this letter starts with a copies of the first letter, and this one starts with b copies of the first letter, and because this guy comes before this guy in the dictionary, we have that a is greater than b. Okay? And so this is xs plus 1 to the a times other stuff. And that means that when I look at this expression, then it's possible that the letter xs plus 1 appears, but it's going to appear to the power a in the numerator and to the power a in the denominator, so it gets cancelled out. And so that's how that goes. Okay. And that's the end of the proof of my lemma. Do you guys have any questions about that lemma? Okay. So given the lemma, like I said, it's pretty straightforward to prove the syzygy theorem because I just do this process. And this process this process over there. What am I saying? I'm saying that well, in the first step, we have no idea what letters we involve. So the initial terms of the generators might involve the letters x1 up to xn. We don't really know. But we know that in the second step, the initial terms of the generators can't involve x1. x1 disappears. Then in the third step, x2 disappears. In the ith step, I involve xi up to xn. And that means that in the n plus first step, the initial terms of the generators involve nothing. They don't involve any letters. Okay? And that means that they're constants. Okay? Yep?
So what if our module has less than n generators? We don't have to use all the variables. We can treat a module such that generators are less than us, right?
Well, the number of generators might be huge. I mean, there might be a million generators here. We don't really know. But it's the letters that we keep track of.
My question is, what if it doesn't involve all of those?
Oh, if this guy, I should say possibly involves. But if x1 is already missing from here, then x2 is going to be missing from here, and it's just going to be shorter.
Right.
But in the worst case, I'm going to involve all of them, and it's going to take me n steps. But in another case, if I don't involve all of these variables, then this is going to finish sooner.
Should it be a free resolution at most length then?
Yeah. Well, the thing is that if you have something that's of length less than n, you can attach 0 modules to the left and make it.
Okay.
Technicality, it doesn't really matter, but let's say less than or equal to n, which is kind of what we have in mind. Okay. Now the point is that you can't really have a constant syzygy, because you can't have a constant times a syzygy equals 0, because these guys are free modules. Okay. So this guy, if it has constant terms, they have to be 0. That means that the nth syzygies are 0, which means that after n steps, we're done. We can put a 0 here. Okay. That's the proof. And it's a constructive proof. It tells us basically that what we've been doing is going to work. So if you haven't done your homework, well, now you know that you can do this and it's going to work. It really is going to finish. Okay. Any questions about Hilbert's syzygy theorem?
So we don't need to be listing any variables on the first step to use x1 on the second step.
That's right. Which is maybe a little bit surprising. But it's what happened here, right? Here we weren't missing any variables. And then in this step, we lose x. And we always are going to lose x in this first step. And in the next step, you're always going to lose y, and etc. That's how it works. Now, I should tell you that if you're algebraically minded and if you're very excited about this theorem in itself, then actually there's a harder theorem, which is this one. You can get rid of the condition of being finally generated. How did we use it? Well, we kind of use it in the first step, because in the first step we said m is generated by something, and the list was finite. And we used that list to say that here we only had one generator. But it takes more work if you want to prove this in general, but it's also true. And it really takes you into a little bit of an excursion into some serious homological algebra. And if you're interested in this kind of stuff, that this might be something that could be the beginning of your project, is understanding this. But we're happy with this. We're happy with this basically because I told you that this is a combinatorial commutative algebra class, and combinatorics things tend to be finite, and that means that generally all these things that we are going to define, by nature, they're going to be defined in a finite way. They're going to be finally generated, generally speaking. Okay. So let's see what else. So we proved Hilbert's syzygy theorem, and now we can use it. Well, maybe before we use it, I also want to write out more explicitly what I was telling Steve a second ago, which is this, that an R module, so we're still in this case, right? So an R module has a unique, and I'll say what I mean by unique in a second. A unique minimal free resolution and what I mean by unique is basically up to isomorphism of modules. Okay, so but there is a notion of just the smallest that these numbers can be, for example. Okay? It's a little bit technical to specify exactly what I mean by this theorem, but again, it's something that if this interests you can look into it for the project. There is a unique minimal way to do this, and so these numbers b0 up to bt are well defined, and they are the unique minimal choice. Okay? So these b sub i's are called the Betti numbers of M. So M was my module that I'm resolving, right? So this is the ith Betti number of M. And it also means that the syzygy modules really are well defined I mean, there's kind of a unique minimal syzygy module. And I can this is well defined, and it's called the ith syzygy module of M.
Is that, what's a Betti number?
It's the number that appears here.
Okay, that's by definition.
Yeah. And the definition of syzygy module is, by the way, what is the syzygy module? Well, for example, what's the syzygy module here? The syzygy module is, you can think of it as either the things that kill this guy, right, the kernel of this guy, or you can think of it as the combinations of the basic syzygies, the image of this guy. So you can think of the syzygy module as either being the image of this map or the kernel of this map. And that's why I define it to be there. So the ith syzygy module is the image of the ith map, which is the kernel of the next one. Okay. So this is just some definitions also, okay. Some terminology. And these things depend only on M. Up to isomorphism. And so now I can give you a bit of a better answer to your question. what about these numbers? Well, what I can tell you now is that if I start with if I start with this ring and any module over it, then I can say that these numbers are well defined in this way. For this example, they do happen to be 1, 3, 3, 1. For the example that you did, it does happen to be what you think it is, probably. Well, I don't know what you're going to turn in, but I think that the natural generalization of this is the minimal solution. And so that's how that goes. Now, I want to just finish by stating a theorem to get you excited about this Hilbert syzygy theorem. And it says this. It says if a graded module M has a finite graded free resolution that looks like this. I shouldn't say if it has it, because we know that it has it. Right? We just proved that. So if, well, it's a slight lie, but if you have a resolution into free modules, so I'm going to call it F0, F1, FR, 0. So if this is a graded free resolution, then the Hilbert, then you can get the Hilbert series of this guy immediately. It's this Hilbert series minus this Hilbert series plus this Hilbert series minus this Hilbert series, etc. And the beauty about that is that it's very easy to compute Hilbert series of free modules, and it's not easy necessarily to compute it for random modules. And this is one of these properties that I'm telling you. This immediately allows me to compute the Hilbert series of this guy to be the alternating sum of the Hilbert series of these guys. Well, alternating, so that means I need a sign, right? Minus 1 to the I, Hilbert of Fi. Okay. And the point is that this is what we want to compute, and these are very easy, as we will see next. So in other words, by virtue of knowing how to compute free resolutions, the question of computing Hilbert series becomes much simpler. So by the way, if you want to solve the homework question about finding the Hilbert series, you could do it using this. The only thing is that you would have to look at the notes and see exactly what I mean by graded free resolution. There's a very slight technicality that it's not difficult, but it means that you can get the answer wrong if you don't take care of it. But this, I think, is a beautiful application of free resolutions. So we'll talk about it next time.